We are going to look at different methods of solving systems of equations. So systems of equations are where we have multiple equations with multiple variables. You probably have dealt with systems of equations where you had two equations and two variables. If we have two variables, then we know that it is a line. And so there's three possibilities when you're graphing a system of equations that have just two variables. So if you graph these equations, change that. One thing that could happen is, and I'm just doing arbitrary lines in here, we could have some graph where the intersection, notice these two lines, are only going to intersect in one spot. And so this point is the solution to that system. So this has one solution. The other scenario that could happen is when you graphed the lines, it ended up being the same exact line. So actually it's the same exact equation, right? It just might not look like it at first. And so if you graphed it and it was the same line, then any point that fell on that line would be a solution. So there's an infinite number of solutions. That doesn't mean any point is a solution. It means that any point that falls on the line is a solution. And so we have an infinite number of solutions. Usually how you would kind of denote this is it's a set of all points x, y. So that set notation is kind of that curly bracket, x, y. Then I'm putting a vertical line, which means such that. And then just put in one of the equations of the lines because they're both the same equation. So like y is equal to whatever the equation is, y equals mx plus b. So it's saying it has to be a point that falls on that line in order to be a solution. The third possibility, and these are called consistent systems because they have a solution. They also even have even more descriptive names. This is an independent system. They're kind of independent of each other, except for that one point. I think of it that way. Dependent, they're both the same line. They both lie on top of each other. They depend on each other. So that's how I kind of remember dependent system. And then the last system has no solution. So what's happening is we have parallel lines, but different y-intercepts. And so if we graph parallel lines with different y-intercepts, notice that those are never going to intersect each other. And so there's going to be no solution. And this is called an inconsistent system. So you should have dealt with these systems of equations before where you're solving for a solution. And you did that by either the elimination method or the substitution method. A little harder is when you get into more than equations than the two, and you have more variable than two. So if we have a system where we have three variables, x, y, and z, they're not lines anymore. What they are like planes. I kind of think of it as a sheet of paper that goes on forever in all directions. And so there's different type of scenarios that could be happening if we graph these. We're not going to be graphing these, but we're going to be finding the solution. So I want to show you what type of solutions you are finding when you're looking at this. And so I pulled a picture up of what could be happening when we're looking at solutions to a system of three equations and three variables. And so notice here we have three planes coming together, but this first picture in here, they're only intersecting at one point. And so just one point is going to be that solution to that system. If we plugged in that point into every single equation into that system, that would satisfy it. It would be a true statement. So you might be asked, is this a solution to the system? You would have to take that point and plug it in for every single equation and show that you get a true statement, like 4 = 4. If you plug it in and it doesn't work for one of the equations, then you could stop and say, no, this is not a solution. Here's a case where we have 3 different kind of planes, but they're not intersecting ever at the same spot. So in here, there's a line that 2 of the equations meet, or here 2 of the equation meets, or 2 of the equations meet, but they're not always meeting at the same place, all 3 of them. Where this is a case right here, that this line in here is where they all meet. They're intersecting at a line. So any point on that line would satisfy the system. So here's some more examples of what could be happening with no solutions. You might have parallel planes, not going to intersect anywhere. Same thing here. There's a line where 2 of these planes are intersecting, but not all 3. This first example in these pictures on the corner, there's only one solution. Here, there's an infinite number of solutions because they're all 3 intersecting at this line. And the bottom one, there's 3 cases of no solution. So we're going to be dealing with these 3 equations, mostly 3 equations, 3 variables. And instead of using that elimination method and that substitution method, we're going to get into a new method of using matrices to help us solve these. And it makes our life so much easier, I think, using matrices to keep things in order. We're pretty much doing the same thing, but not having their variables in there. But before we do that, let's kind of look at this with not doing matrices, and I think we'll have to definitely wait until our next lecture to look at how to solve these with matrices. But let me pull one up and let's look at solving it without matrices. And it will kind of hopefully remind you how to do this with substitution and elimination method. Okay, so we have an example in front of us, and looking at these, I just mentioned that these are tedious, and so it's really important to make sure you wrote down the equation right. So we have 2x plus y equals -4. Second equation, we have -2y plus 4z = 0. And third equation, we have 3x minus 2z equals -11. Okay, so I copied that down right. Our goal right now is to get 2 of these equations to have the same 2 variables. And so looking at this, I noticed that none of them have the same 2 variables in there. First equation just has x and y, second equation has y and z, and the third equation has an x and a z. So what we can do is let's solve for one equation for one variable and use substitution. And so looking at all of those 3 equations, I noticed that first equation, it would be easiest if I solved for y, because that coefficient in front of the y in that first equation is 1. And so I don't have to divide by a coefficient and get fractions. So let's look at this first equation and let's just solve for y. Get y by itself. We would get y is equal to, we would subtract 2x on both sides, -2x minus 4. So let's go into our second equation, because that's the only one that has a y in it. The third equation doesn't have a y in it. Let's go into our second equation and let's do substitution. So we're going to go in and we're going to substitute in what y is, wherever we see a y in that second equation. So let's just rewrite this with a parentheses where we see the y. So we have -2. I see a y there, so let's put a big parentheses, plus 4z equals 0. So we're going to go inside and plug in -2x minus 4 inside that parentheses. So let's now distribute that -2. combine like terms and solve for x. Or no, actually, we won't solve for x. Let's distribute that -2 and then simplify if we need to. So distributing the -2 to both terms, we get -2 times -2x is 4x. -2 times -4, so that's +8, plus 4z equals 0. And so notice that I have the same variables that I do in that first equation. Let me just isolate the variables and get that 8 to the other side by subtracting 8. So I have 4x plus 4z equals -8. So basically what I just did is I manipulated this. I'm rewriting my system to have, it's a new system, but it was going to have the same solutions. And so this is my new, and I'm going to just call them rows. This is my new row 2. When let's just leave that there. Let's keep this as our new row 1. And row 3 is the same. So if I rewrote this system, y is equal to -2x minus 4. We have 4x plus 4z equals -8. And we have 3x minus 2z equals -11. So I'm going to use the elimination method, or another word is called the addition method, where I'm going to use these two equations that I just manipulated that we'd have the same variables. So I'm going to multiply something by one equation so that if I add the two equations, either the x or the z would fall away. And so notice if we multiply this third row by a 2, I can make this a -4z, and adding it to that 4z, that equation above, that z would go away. So let's multiply -2 times row 3. So let's rewrite this, multiplying this whole row by -2. So -2 times 3x is -6x. -2 times -2z is plus 4z. Oops, I don't want -2, I want +2 to make them opposite signs. Okay, so multiplying by +2, we get 6x minus 4z is equal to -22. And I want to add this to my row 2. So let's put our row 2 below that. So we have 4x plus 4z equals -8. So if we sum these two rows, we would get back 6x plus 4x is 10x. The z's cancel, which we wanted, equals -30. So in here, I can see what x is equal to. Divide both sides by 10, we get back -3. And so we want to go in and we want to figure out what y is and what z is. So there's a couple ways we can do this. We can do back substitution. So I notice right away, if I plug this back into my first equation, we could figure out what y is. So we know that y, right, is equal to -2 times x, which we just found, minus 4. So we get y is equal to 6 minus 4, or y is 2. So now we have x, y, we need to figure out what z is. And we can figure out what z is by, again, doing back substitution. And so we'll go into one of the equations that has a z and plug it in. So we can plug it in to this equation, we can plug it into this equation, whichever one we want to plug it into. I usually would just look at what's easiest if there looked like what there was one. Let's just use that second equation up here. And so -2, parentheses, because I'm going to plug in what y is, plus 4z equals 0. but y was positive 2. So let's solve for z there. We got negative 4 plus 4z equals 0. Let's add 4 to both sides. So we get 4z equals 1. Divide by 4. Actually, add 4 to both sides, sorry. We get 4z equals 4. Divide by 4, we get z is 1. So our point, that's a solution, and it's in the form of x, y, z, is going to be negative 3, 2, 1. So if you plug those values in for x, y, and z into our original system, for each equation, that should come out as a true statement. And we could test it and check it, but we're out of time, so I'm just going to leave it at that. So I just wanted to quickly go through that 12.1, just kind of as a reminder of how to do systems of equations. But next time we're going to jump into 12.2, which is what section it is in our textbook, and look at using matrices to solve this. So it's kind of a similar idea, but we're going to be doing this without having to have our variables in there.